So we move now to the last talk before the coffee break, which is given by Professor Alex Retzker from the Hebrew University. He's also a principal research scientist in Amazon. And the title of the talk is Erasure Qubits for Quantum Computation. Thank you, Adi, and thanks for the invitation. It's always a great pleasure coming back here to Tel Aviv, where I've done my PhD together with Lev and Benny. Okay, so I will talk about Erasure Qubits, which is work that I've done as part of my work at Amazon. Before that, I just introduced myself. So I lead the quantum theory group at the Hebrew University, and the work we are doing is always strongly connected to experiments. So like 10 years ago, I was mostly around quantum sensing, and then I founded this company in Germany, Envision, which is doing quantum sensing. I mean, so this conference is more about quantum computing, but you have to remember that quantum is also quantum sensing, which is also a very developed field, and this company already has products which we sell. And like a few years ago, my interest switched back to quantum computing, where I joined Amazon, the Amazon effort to build a quantum computer, and so lots of things that we are doing in Amazon, and this is something that I can actually talk about, which is the Erasure Qubit, which is work that I'm doing. So we'll start with an introduction, or kind of state of the art of the field. So there are a few contenders for building a quantum computer. So it's a very kind of very interesting competition. One of the new players and very promising is the Rydberg. It's built out of atoms. That's how kind of an atom array looks like, and each atom is a qubit. And there are a few startup companies who are kind of pushing the field. And in recent 2 years, there are really kind of amazing results, which I'll briefly discuss later on. Yeah, these are the kind of the startups that are pushing this. Ions is a relatively old and established field for quantum computing, which is quantum computing with ions. That's kind of a schematic picture of an ion-trapped quantum computer. Each ion here, each dot here is a qubit. Again, both for atoms and ions, each quantum bit is a single atom or ion. It's a relatively developed field, been around for a long time, and they have really impressive results, which I will describe briefly. Also for ions, the main players are actually startups. So for atoms and ions, the main players are startups. For superconducting, which is maybe the most kind of advanced field right now, the main players are the big corporates, and that's what gives kind of a huge advantage to superconducting. That's why it's kind of, in a way, it's ahead of the others. And yeah, it's interesting to think what's the reason for that. But I guess, at least my point of view, is that the reason is that in the end, the superconducting architecture is just of electric circuits at low temperature, but electric circuits. It's kind of much easier to explain to people who are doing computing. Conceptually, it's not so much different. There's also a fabrication facility, which is in the center of activity. It's not so much different than classical computers, so these people are willing to invest, are willing to push the field forward. It's much more difficult for atoms or ions, which is kind of a very special thing that it's very hard to explain to people outside the field. And I will start by kind of reviewing the state of the art of these technologies. There are another two technologies which are very promising. So Chaim discussed the photonic one. Also, there are startups in this field. PsiQuantum is kind of the main player who's pushing the field. It's a bit harder to discuss the state of the art of this because at least this company, which is the main company, is working stealth mode. So it's not totally clear what they have, even though it's a very promising technology. They did publish a paper recently about the silicon effort, which is impressive, but it's not the main effort. The main effort is silicon nitride, and I don't really know what the state of the art there. Again, this is very promising, but I can't really compare it to anything. The other one is, it's one of the main advantages is actually done in silicon. The other silicon effort is quantum dot, spins in silicon. also very promising, but also works in a semi-stealth mode. There's HRL, there's Intel. Not a lot is known, more than in photonics. So it's a promising thing, especially as fabrication goes. But again, not enough is known to compare it to the others. Okay, so now review the state of the art of like the three main technologies. Ions, which has been around maybe longer than the others. Yeah, there are electrodes, there are lasers that manipulate the ions, but the basic ingredient is the ion itself, which is the internal states of the ions. These are the qubits, so usually pick two states, can be a ground and a metastable state, which live for a long time, and this will be the qubit, and other states which are unstable, which helps us to measure the state of the qubits. It's possible to manipulate and measure with lasers. Some do it with microwaves, so technologically there are some advantages to that. But in principle, that's how the manipulation is done. The gates are done via interaction with this vibration of the crystal. So the ions, they form a crystal, this crystal vibrate, and they behave in a quantum mechanical way, so it's possible to use it to create gate. The path forward of scaling is basically create some kind of electrode structure in which these dots are the ions. They can move around. They can kind of sit here. You can do gates between them. Then they can move around. Suppose this one will move here. This one will move here. You make a gate and then move back. And this is kind of the big idea to scale it up. This idea has been around for 20 years or so. And right now we see kind of first results for Quantinium, which is a spin-off from Honeywell. It's a startup. Very impressive result. They still don't have this structure, but they're on the way. They have kind of this structure we call the racetrack. So if you want, suppose this qubit to interact with this qubit, it has to move around all this way to jump, hoop over all the others, make a gate, and then hoop over back. Just the racetrack architecture is kind of easier to do, but the next stage would be really this architecture which was proposed 20 years ago. They're really following these ideas that were put forward. My people came from Boulder, from the Boulder group, and they have very impressive results. The recent results, they have 56 qubits. The infidelity is the best. It's 0.15%. Also with microwaves, there are kind of comparable results. Microwaves, ions with microwaves. So they are really kind of below the threshold. The threshold is around 0.7, 0.6%. They are below the threshold. And that's why they actually can show already logical qubits. They can show the error correction works. And what error correction should do, it should take these physical infidelities, so here like around 0.1%, and improve it by kind of combining many physical qubits into big logical qubit. And they did show now, recently some results. The physical qubit has an error which is, so the logical qubit has a smaller error than the physical qubit. By around an order of magnitude, depends, they've done lots of experiments, depends exactly how you look at it, but 1 order of magnitude smaller of an error. This is really a milestone result. And the important thing is that it's the first order of magnitude which is difficult. After that, it becomes easy. So they really made the important step to go from here. Theoretically, it's easy. It's just that this racetrack architecture is not good enough because there's not enough qubits, so you have to go to this different architecture of electrode. But the principle is the first order of magnitude, which is the difficult one. Then it's easy. So they're really on the right path. As far as I understand this technology, they're really on the right path to show results. Problem is, the technology is relatively slow. And the price for that is not totally clear at the moment, but it can be a significant price to pay in the end. Superconducting, this is maybe the kind of technology or the effort that kind of got more attention than all the others, and there was much more effort put into that. And again, one of the advantages of this, in the end, it's an electronic circuit. It's just an electric circuit with an extra component junction, but in the end, it's an electric circuit, so it's kind of easy to explain people from computing to doing fabrication, to doing classical computation, what needs to be done. And you can quantize it, and you can look at the two lower levels, and this forms the qubit. And it's interesting to see this effort in the last 10 years or a bit more, kind of the competition between IBM and Google. IBM went for kind of a technology in which these are qubits, which they interact directly. There's no on and off button. They're always interacting, so it's kind of, in a way, it's not a modular technology. It's not, maybe it's not an engineering way of thinking. There's no modularity here, but in principle, theoretically, by fine-tuning, it can work. And the idea here is that you have these two qubits which are coupled together, and you suppose you drive this qubit. And if you drive this qubit at this resonant frequency, you will change the state. This is a single qubit gate. But if you drive this qubit at the resonance frequency of the other, you will move the other one. And that's a two-qubit gate. Okay? So these two qubits, they always interact. There's no on and off button, except your drive. In principle, it should work, but it's non-modular architecture. There's always interactions, there's always terms that will induce errors, which you should fight somehow, some complicated control, but there's always also, in a way, it's not a modular architecture, in a way, it's not maybe an engineering frame of mind. What Google did is something different. They added a coupler, and the coupler, its role is to turn on and off the interaction between the two qubits. So it's a bit more complicated, but it's modular. If you don't want the qubits to talk to each other, they don't do that. At a very good precision. And in the end, it looked like the Google architecture is better. The IBM, we kind of were stuck with this lattice, which is called heavy X, which has disadvantages for error correction, but the fidelity, which is above 1%, which is not enough. But they did manage to build a very good fabrication facility. What Google did is this experiment, which is really kind of a milestone experiment. So these are physical qubits, and you can form a logical qubits from this patch here, or you can form a logical qubits from this patch here. So it's a bigger one. And if the error of the bigger one is smaller than the smaller one, then it means you already see what is called sub-threshold behavior. Still not a break-even. Still the physical qubit is better. So the logical qubit is not better. But the bigger you make the logical qubit, the smaller is the error. It means that error correction works. It's not as impressive maybe as the ions, but it shows the scalability is working. It shows that error correction is working. We have to scale it. And indeed, that's what they've seen. This one, the big one is better than the small one because the error threshold, the error is exactly at the threshold, is 0.5%. So they're kind of on the verge of break even. So this is kind of arguable, but they're more or less there. But the important thing that here they're actually at the threshold. Their errors are exactly at the threshold. So it's almost working, or you may say it's working, but the point is that further you go away from the threshold. Suppose the threshold is 0.7%. You can make a lot of effort to go to 0.1%, and it's a big difference. You can go and improve it from 0.1% for 10 to the minus 3 error. So it means that every time you do a gate, for every 1,000 gates, one gate will fail. You can work hard and you can improve your system and go to 10 to the minus 4. So it means every 10,000 times you're going to do a gate, one will fail. You will gain, but not so much. You can also improve from 10 to the minus 5, from 10 to the minus 4, 10 to the minus 5. You will gain, but very little. But it's the first order of magnitude from the threshold, going one order of magnitude down. This is the tricky part. This is the difficult part. And this is the part that gives you the gain. And the question, how do you do that? Okay, so I will describe later on our solution to that. So basically what happened, and it's interesting to see, is that IBM kind of moved to a different architecture with a coupler, kind of they had their own ideas, but it's kind of in the spirit of the Google architecture. And now they really have impressive results. Yeah, so this is the same fidelity. So it's like 3.7, 10 to the minus 3, and they're improving it. And eventually, probably they will show really in the next year or so quite an impressive result of error correction. It is fast. So the cycle time is around the microsecond compared to more than 100 for like the other architectures of ions and atoms. It remains to be seen what is the price of this 2 orders of magnitude difference. It's not totally clear, but it can be very significant. So there are like maybe a few things to learn from this is that first, it doesn't really matter what you do. The one who has the advantage is the one who has the best fabrication facility. The others' ideas are important, but not as important. And the other thing is it's maybe the modular architecture is the best one. So what you want is when 2 qubits are doing an interaction, they should not interfere with the others. And then turned out to be a critical point. And maybe it's kind of a more engineering viewpoint of this endeavor. Maybe is the right one. You have like modular things to get modularity. In the end, this concept won. But again, what is in the end is really important is the fabrication. In neutral atoms, they kind of emerged only a few years ago. Nobody took them seriously up to a few years ago, but the results are quite amazing. And the way it works is with kind of optical trapping, with optical tweezers. It's possible to control the single atoms, move them around, and make gates with them. And that's what they achieved really recently. So they have also good 2-qubit gates fidelity on the order of 0.6%, kind of comparable to superconducting, again, at the verge of the threshold. Really at the verge. So you should make this extra effort to bring it kind of below 0.1%. And after that, it doesn't matter so much, probably. But they are kind of, they got to the threshold, and the question is how to improve it. The experiments are very impressive. They already show some logical gates. And the reason that this is relatively simple, that's why kind of they're progressive extremely fast. So each square here is a logical qubit, which is composed out of a few physical qubits. And if you want them to interact, you bring, suppose, the logical qubit from here and from here. So this is an atom, which is, so that this atom will talk, suppose, to this atom, this one to this. That's what you see here. And just with one laser pulse, you just make all the gates. So it's a kind of, again, very modular architecture. When these 2 atoms talk, they almost don't interfere with the others, and it's very simple control. It's just one laser makes all the operations. So in terms of kind of engineering, this is kind of considered very simple. And they do have ideas how to scale up. They want to connect it with cavities, with photons, and then to connect between different tracks. But 2 of these technologies are really at the threshold. And also the ions, they're not so far away, and also some other ideas can help a lot. And that's where this work is coming to play. These are kind of the ideas that we were pushing recently. One of the big limits of fidelity, of error, is just that most qubits, they tend to have what is called amplitude damping, tend to decay. So when you put a qubit in the excited state, after a while it will decay to the ground. And this process of decay, it's very bad for fidelity. It limits your fidelity, and there's not much in principle you can do except just to make your gate faster and faster. And because there are kind of physical constraints to the speed of the gates, you just stuck at some point. And this is the reason that kind of 2 technologies are stuck very close to the threshold. So what can be done? And this is our work. And what we propose to do, together with others, so there's like a few, this is kind of a new direction that a few groups are pursuing. I will kind of show the other groups. this our work, and what we propose to do is to design the qubit in a way in which the error is an erasure error. So it's an error that you know that happened. Now, I will explain the next slide why it's so important. But if you know where the error happened, the way you correct errors is that you make many, many measurements. These measurements give you lots of information. It's which kind of error has happened and where it happened, and then you can correct. But this number of measurements, this is the thing that actually sets your threshold. That's why the threshold is so restrictive. It's around 0.7%. And the reason for that, you have to make many, many measurements in order to find what kind of error has occurred and on which qubit it occurred, and then you can correct. If you can design your qubit in a way that you know where the error has happened, then your threshold suddenly goes up, and your actually logical qubit behaves in a better way, which is called, it has a higher distance. And so how does it work? If you look, this is kind of the main equation of error correction that connects a physical error to logical error. There's always a threshold, so it's for the surface code, for the code, most people use it around 0.7%, but this is more or less the ballpark of numbers. And this is the physical error. So you should be below the threshold, and if you are below the threshold, then you get exponentiated by this d, which is called the distance, d plus 1 over 2, and then this is the logical error. Yeah, so you get, so once you are below, so you have to go below the threshold. That's why the reason the results in many technologies are not so impressive, because the physical error is very close to the threshold. So you should bring it down somehow, like an order of magnitude. After that, it doesn't matter so much. But you should bring it down somehow by an order of magnitude. Erasure qubits, they behave in a bit of a better way than that. So qubits in which you know where the errors happened, and this is kind of a typical picture of a surface code. I will discuss it in the next slide. It has two main features. First, the threshold is not like 1%, 0.7% by 4%, so this number becomes larger. And I will show that this number becomes smaller, the physical one, but also the effective distance, this factor here, becomes larger by a factor of 2. I will explain why. So basically, we gain from two things, from the threshold, or three things. The threshold becomes better, the error becomes smaller, and we put it by power, which is higher by a factor of 2, which is very significant. Okay, so what do we need? We need erasure noise, that really this decay is the main noise. We need errors which are detectable. And I'll explain how it's possible to do this, and then we can build these erasure qubits. So why is it so important? What you see here is a typical picture of a surface code. Each point here is a qubit. And each square here is a measurement of its parity. And that's how the surface code works. Suppose we make many parity measurements. Now suppose these two qubits, they are wrong. There was an error here. So the parity of this square will not change because it's changed by 2, but the parity of this square did change because it's changed by 1. So this flag here will be flagged, and we know that there is an error somewhere here. If it's the only one that is flagged, we know the error is here. Now suppose these two are flagged. So there are a few options. Either there is an error in these two, or error in these two, or there is an error in these 5 qubits. It will give us the same error, the same flags will turn. The same plaques, the same parity measurements will be flagged. So we'll not be able to distinguish. But if we knew that the errors, and what we will assume, we assume there's a higher chance that 4 qubits made an error than 5. So we'll assume that these 2 made an error, this one will, and we will correct them. But it means that if there are 5 errors, then we cannot correct. If these qubits were flagged, if we knew that the error happened here, if we knew that, then we could have corrected. And then the role of these flags is only to find which kind of error happened. And that's what actually improves the error correction considerably, and that's what we claim is going to be the extra ingredient of bringing this error down from the threshold to 1 order of magnitude lower, and then bring us to the realm of kind of logical qubits in which we can do logical memory and logical operations. Okay, and this is important for a few technologies. So these ideas that came from the neutral atoms community, here they have levels which are metastable. They are not stable. So if this is the qubit, this one, or they always have to use a metastable level, a level which is not stable, which decays really fast. And what happens now, it decays exactly at the error which limits your error exactly at the threshold. And the idea here, if you can, suppose when it decays, it can decay back here, but this is a very tiny probability. Usually it decays to some other level. If you can find that it decayed here, suddenly your error becomes an erasure error, and then you gain the missing order of magnitude in error. And then you're deep inside the error correction limit, and you can correct and you can do computing. The same ideas were in the superconducting platform. One is kind of from Yale, in which they use superconducting cavities, and one from us, in which we use transmons, which we use qubits. Kind of the ideas are kind of similar in nature, and in the few minutes I have, I will explain the idea. Okay, so I'll skip this one. And the idea is the following. So how do we want to do it? Okay, so suppose we have a qubit, and our qubit gets zeros and ones. But now we want to take two of them. And if we take two of them, our qubit is going to be 0, 1, or 1, 0. So our qubit is going to be, we're going to take two qubits, merge them together, and our qubit is going to be either the excitation is in one qubit or the other. This is the qubit. But if there's no excitation whatsoever, if there is a decay, it goes to the 0, 0. And if we can measure the 0, 0, we will know if there was an error or not without interfering with this qubit. So we know that we cannot, we're not allowed, when we're making the measurement, we're not allowed to interfere with the qubit. We can't just measure the state. If we measure the state, the qubit is gone. But if we make a measurement, is it in 0, 0, or is it in one of these, without asking, is it here or here, then in principle, we have our erasure measurement. Okay, just a few minutes, so let's skip this. Okay. So again, the idea is the following. We take two qubits, and this is how a superconducting qubit looks like. And the qubit here is there excitation here or not? Another qubit, is there excitation here or not? And we form kind of a hybrid qubit between them. So our qubit is the excitation on the left side, or the excitation is on the right side. Okay, this is going to be our qubit. If we measure and we see there's no excitation whatsoever, we know that the error has happened. But we should measure it in a way, so we are allowed to measure, is there excitation here? Did the excitation decay? But we are not allowed to ask the question, is the excitation here or here? If we can ask a question like this, if we make a measurement like this, then we have our erasure measurement, we have the erasure qubit. Then we can correct errors. Because if there is a decay, the decay will go from this 0, 1, 1, 0 to 0, 0, and then we should be able to make this measurement. Then we should find ways to control this qubit. And we did show that we can actually control this qubit with very good efficiency. Okay, so I have, how much time do I have? 1 minute. Okay, so if I have 1 minute, I'll just show you the, okay. Lots of things happen here, but okay, but I'll show you the final result. And the final result is the following. In our case, we have an erasure error of 0.44%. So really, really close to the threshold. But now we convert this error to erasure, which means the error, the threshold is 4%. We're one order of magnitude below the threshold. One order of magnitude below the threshold is exactly what you need. You don't gain so much by going below that. The residual errors, the ones that actually will cause us problem, is 0.01%. So deep, deep inside the threshold. So basically, we kind of converted this error, which is exactly at the threshold, to two different errors which are considerably below the threshold. And now we're hoping to take it to the next stage and actually create a logical qubit out of this. And my time is exactly up. Sorry? Okay.